Good evening, everyone. I welcome you to today's webinar, which is a part of the training and the capacity building for a short program. Before I welcome our today's guest expert speaker, I would like to just run through what is a short program and what are its four tracks, and then we will start with our webinar. Assure, the acronym stands for Accelerating Sustainable Super Efficient Real Estate. It's a joint venture with Infosys and IHS coming together to make an effort to change the real estate landscape and promoting high performance buildings. So we are looking at actually guiding the real estate group in the commercial category to help them understand that standard buildings can now move to the next level of high performance buildings at no additional cost. There are four tracks under Assure program where we are looking to give pro bono technical advices to projects which are new construction or retrofit, where we would help and guide the team to understand what are the nuances of high performance building design and how do we achieve it. So we have a KPI list and we'll guide the entire team. So if you have any projects, whether be it new construction or retrofit, please write to us and we will have a conversation and see how we can take it further. The second track is the training and the capacity building, where we are focusing to upskilling professionals from the industry. So the target is about 12,000. We have been having webinars and we have been having, workshop immersion programs at different places in India every month. So please check our LinkedIn handle, and we have a upcoming program which is happening in Bombay, and it's again a pro bono. Please be a part of it. You will get to know and learn a lot of important things of building design. The third part is the market adoption of high performance buildings, where we are looking at innovation, creating a performance verification and measurement platform, and welcoming innovators where we can guide them, mentor them, take them to the products which can be used for this high performance building. Lastly, the data, what we will be receiving from this lighthouse projects, we look forward to have or develop a conversation with the center or the state government to understand if we can work on some financial incentives for projects which are adopting high performance methodology. We're looking at a greater impact which will change the entire building industry, because it's one of the largest contributors to the climate change. And these are some of the numbers which we look at the success or the measurement of this program. Today's speaker is also our faculty in the training program, Samit Bhowmick. He is the director and co-founder of Vera Tatwa, which is a project management and a design consultancy firm for MEP. He is a mechanical engineer and his passion lies in high performance buildings. And today he's going to touch the most important topic about how small common sense things about HVAC design in buildings can help you to adopt these high performance techniques in your building and learn about them. He has more than 25 years of experience and he has worked in all the sectors from power plants to clean rooms to commercial buildings. And one of the really leading firm which looks at high performance buildings by genuinely, trying to make an impact. And I look forward to this session. Welcome, Samit, sorry.
Thank you,
Yeah.
Sandhya, and welcome everyone.
Samit, you'll
Uh,
have to be a little louder.
Loud. All right. How about this? Is it fine?
Yeah.
All right. Good evening, everyone, and welcome to this webinar. Thanks, Sandhya, for the introduction. You pronounced my name in Bengali right. So,
Thanks.
all right. So, All right. So what I'll do is, let me just quickly share my.
Yes, your screen is visible.
All right. So today's topic is common sense strategies, and this is something which I'm personally passionate about because sometimes we tend to get lost in a lot of technical stuff. And what I'll be trying to share in this next few slides is some of my own experiences. I interact with a lot of architects, engineers as part of my practice, and some of the frequent questions I have to encounter. I'll be talking about them in this next few slides. So we'll go through them and probably we'll have a little bit of question and answer at the end if any of you have questions and want some clarifications. And I think that should be the general format. All right, so Sandhya has already talked about me. I don't need to talk about myself anymore. All right, so we jump straight away into the content and strategy. My strategy number one, and something which is very, very, feels very intuitively necessary, but frequently, overlooked is load profiling. And I talk, a little bit about this, and just take a look at this slide and try to sort of grasp information on this. So a typical sort of a university campus, we have different kinds of blocks, and all of you will be familiar with this: hostels, classrooms, administrative block, and staff, uh, faculty. So you will typically we would want to, we know that all of these buildings don't usually operate at full capacity throughout the year or throughout the day itself. But I found this very frequently, missed out during design. And if you look at these numbers here, one might think that 450 tons should be the cooling plant size. But luckily, luckily we have this benefit of diversity, which is, like I said, very frequently overlooked. And by diversity, we mean the ability or the reality that buildings do not operate at peak loads at all points of time, and therefore we expect, so for example, in this example, the hostels and the staff housing to be not fully operational during the daytime, and therefore a 450 ton could be properly sized to 300 tons. Now, there is no thumb rule for this diversity. Uh, what I would sort of recommend and something which you should probably work toward is, something like a load profile, which gives you a, probably an hourly trend or a seasonal trend or maybe an annual trend as well. So on this, you can actually plot out the the coincident cooling loads from different buildings. And in this particular example, you see that it's 316. So like in the previous slide, we roughly arrived at 300 tons. A more accurate analysis can bring you to a sort of more reasonable figure of overall cooling load. So diversity, uh, absolutely essential. We tend to always add them up, but very rarely do buildings operate in that fashion. And so you have the opportunity of optimizing your cooling plants if you look at diversity and ask for the questions that will lead you to the right cooling loads. So what we gain by working on that is, not only a smaller plant capacity, but obviously you're also spending less. And when we're talking about high performance buildings, this is very important because in general, people will be saying that, whatever you're bringing onto the table is going to be more expensive, and therefore the aspect of capex is important, and you should be looking at that from day one. Obviously, oversized or heavily oversized systems consume are not efficient, so they do consume not just the capex. You also end up with a higher opex with highly oversized systems. What the load profiling also lets you do is to stage equipment. For example, in the plan in the previous slide, we saw 300 tons. So you could have 300 two chillers of 300, or you could have 150 tons into three. All of these decisions you can take based on the load profile. So our strategy number one, and I think something absolutely essential, is to use the benefit of diversity to optimize equipment plant capacity. So that's uh, our strategy number one for today. Now let's look at the next one. Bigger is better. Bigger is not preferred, I'm sure, by a lot of architects. But when it comes to buildings, let's see what this means. So I think this is common sense. A larger duct will offer less resistance, and something which offers less resistance will have lower power consumption. And it also turns out that it has less noise for the same airflow. This is because, of this formula. No, I know this is a common sense strategy, but this is a very simple sort of formula. It's important to sort of at least remember the relation with that. So the pressure drop in a duct or a pipe is inversely proportional to the fifth power of the diameter, which means that if I reduce the duct dia by half, the power consumption increases to 32 times. So half and 2 power 5 is 32. So this is a significant impact, and we underestimate this, in our, daily practices. And I've seen so many projects where a lot of the times we are debating about this. But such is the impact of just size on power consumption that one cannot neglect it. And if I try to put this in sort of more perspective, so let's say we have this duct of 600 by 400 millimeters, and I simply reduce the height of the duct for the same flow rate by 100 millimeter. Our power consumption, the fan power consumption increased by 2.5 times. So it is significant, not usually discussed during designs, and certainly not considered when we're looking at false ceiling layout. So what I'm trying to come to is that we don't uh, arrive at a high performance building by just taking one building and trying to build in all the components and trying to make it high performance. You have to start thinking high performance very early. So if you're looking at something like this, we need to realize that, we cannot simply, I know because I've had these conversations very frequently, we cannot simply compress ducts to accommodate a false ceiling height. So you need to start looking at your building heights. You need to start looking at innovative ways of doing the false ceiling if you're thinking of something like a high performance building, because the impact of this is so much. Remember that the pressure drop is inversely proportional to the fifth power of diameter. So it's a very, very big impact, something which we cannot neglect. Very, it comes from common sense, but I very rarely find this being applied in actual practice. This is another trend, I might say, but though it has been used widely in other countries, but this is something which is catching up in India as well. So water, it turns out, is has a higher heat carrying capacity, about 4 times higher than that of air. And because it is so efficient, you can actually use small dia pipes instead of large ducts to remove heat. And this is of great use. We're talking of, say building to building, floor to floor heights and higher false ceiling heights. So this is a one way of doing that. Uh, and it's been used, and I think you find a lot of new buildings, at least in areas which are dry and convenient. Looking at systems like radiant cooling or chill beams, where the chilled water or the cold water is brought as close as possible to the cooling load, and thereby you use pipes, smaller pipes to remove the heat rather than large ducts, which would be conventionally used. So not only are we bringing it closer to the load, because water is now 4 times more efficient, we're also going to consume less energy in doing the same job, right? Strategy 4, location is everything. And I think every one of us on this webinar is probably from the real estate industry. And I think some of you are real estate investors as well. So I think you'll agree to this. Location is everything. But let's look at how this is applied to, our area of work. Take a look at this small office space, very simple, straightforward office with an H room on one side and the toilets also on the same side. So you can find that a lot of architects might prefer this because they're all aligned in the same place, so it's more compact, and they would want to have services on one side. But this has the problem that the exhaust from the toilets might tend to get short cycled into the pressure intakes of the AHUs. I hope everyone's aware of what the AHU room is. This is a room which will have an air handling unit, and the air handling unit draws in outside air. It takes back return air from the space, mixes it up, cools it, and then distributes the air back into the space. So we need outdoor air to remove the pollutants from the space. We also needed to remove the carbon dioxide and other pollutants and other things which we exhale into the indoor air. So it's necessary for us to maintain a certain indoor air quality. And if you have the toilets and H rooms on the same side, there's a very high risk that that objective will not be achieved. So probably one way of solving this is to have it on the opposite side. And like I said, just locating the service rooms in the right place can make a big difference to the experience you have within a space, right? Of course, while we're locating this air handling unit or the outdoor air intakes, you also need to make sure that you don't have polluting sources outside the building. So you need to be aware of what is outside the building as well. But once you've done that, you want to make sure that you don't short cycle the exhaust from the building back into the same air handling unit. Take a look at this layout now. Same layout, but with a different plan now. So with this now, we have two smaller AHUs and we have the toilets in the center of the building. Very common nowadays to see this kind of an arrangement. And because the toilets don't have now any exterior or an external wall, we need to exhaust them to the roof of the building. Now, that sounds very attractive, but in my own experience, I've just found this to work in short buildings, maybe 2, 3 floors or so. But as buildings become taller and taller, it becomes more and more difficult to extract from the lower floors. And you can also see that the ducts start becoming longer. When ducts start becoming longer, you also start consuming more energy for doing the same job, literally. So this is a way, one probably arrangement by which we could, fix this. In general, and from my experience, I found that distributed systems respond better. So if you have, for example, the toilets or the toilet extract fans on the terrace of the building, you might have in a taller building multiple floors. Some of the floors might not be occupied, but you would still run the extract fans, just because all of them are connected to the same, extraction unit. But having them floor wise lets you switch off floors, turn them off in case if you have a multi-tenanted building, you might want to your tenants may or may not be available on a certain intermittent floor. And the system design in general should let you respond to the business need. I think this is something which I'm seeing more and more necessary in the last 4 or 5 years of my own experience, where businesses want flexibility. And traditionally, we have looked at centralized systems where things were all brought to a central location, and we wanted larger and fewer equipment. But in the last 4 or 5 years, I found that businesses want the ability to scale up and scale down very quickly. And it's useful if you start thinking of these services also in a way in which they can be scale up and scale down, and in general to be able to respond to the changing business needs. Next strategy, again, common sense. Uh, we tend to look at ventilation more from a perspective of supplying fresh air. But my own experience and personal perspective is that what we need to look at probably more is effective extraction. We don't really give time to that, but effective extraction, I think, is more effective than just looking at the fresh air side. So let me just demonstrate this with this image. So look, just imagine this tank of water which we're trying to fill up, and we can only fill up water in this tank till it is full. And once the tank is full, we can't fill any more water because there's just no space left in that tank. The only way we can bring in more fresh water into the tank is by removing or extracting water from that tank, right? And we apply the same logic to this space. So you have an office space, you're trying to get outdoor in, the air handling units are bringing outdoor in into the space, and you can only do it till the space is full. And once that is done, unless and until, unless and until we start extracting air from that space, we cannot get fresh air in. So which means if we want to achieve a certain quality of, certain indoor air quality in a space, or we want to make sure that we want to get a certain amount of fresh air into the space to give, probably a healthy environment, you need to also make sure the extraction is matched to it. If that is not done, the ideas only remain on paper, and you will only be able to get into the building only as much as you can extract. So from so the sort of the takeaway from this, I would say, is look at the extraction first, try to fix it, and then try to see if you're doing enough to be able to give you the ventilation that you need, maybe from your standards or from your, whatever you want to do in your design process. Something which I find very commonly neglected, because toilet exhausts are just some equipment which are just thrown in some place, maybe the terrace or somewhere. No one tends to look at how that ties up to the, in how that ties up to the outdoor air that's brought into a space. Again, common experience. I think a lot of people will relate to this. We walk into a hotel room. The first thing we do is switch on the AC, turn on the fan, and then you start feeling comfortable very quickly because they switched on the fan. And this is what we can also apply to spaces. And if you typically what we look at a thermostat is the air temperature, but what we feel really is the operative temperature. And operative temperature is a factor of multiple other things like radiant temperature and air velocity, in addition to air temperature. So in general, what you can do is you can play with any of these components and control thermal comfort. So air temperature we see, but air temperature is not all. So if you have spaces which have very high thermal mass, or you have radiative heat gain into a space, then radiant temperature becomes important. And one of the most important things which we tend to neglect, and because of probably cultural reasons, the HVAC systems, a lot of modern buildings, people, architects generally, or clients, don't prefer to use ceiling fans. But ceiling fans, I think, are a very, very common sense, low cost, and extremely effective way of improving thermal comfort. And there's a lot of science behind it. In a air conditioned space, for example, you can actually use a ceiling fan and enhance the cooling effect by up to 7 degrees. So this is actually research done in IIHS, and papers have been published on this. Your adaptive band, or the band through which across which a human remains comfortable, also is expanded by the use of a ceiling fan. Basically, what we're trying to do is we are trying to uh, change the air velocity, enhance the air velocity, and improve the cooling effect. What this effectively does is that we are now able to run our chiller plants, at much higher temperatures. So if you were operating a place at, say, for example, 24 degrees, you might now be able to run it or set it at 26 degrees. And with the use of a fan, you can start still feeling comfortable. So this has a very, very high impact on energy consumption. So every degree of increase in set point temperatures is about a 3% improvement in efficiencies. And something which is very common in our personal lives, but we tend to sort of not look at this when we're looking at commercial buildings. But there's a lot of new buildings which are happening, and I think a lot of people are getting aware of this. And I can see there's a lot of demand for integrating ceiling fans into the interior. So I think this is something which I'd say very, very useful, very low cost, and extremely effective way of reducing energy consumption. Okay, so how much have we? Right. So I've looked at some of these uh, sections, and I'd like to sort of answer questions if anyone has any. Be- uh, a lot of them might sound to be, something which is intuitive and should have been done, but frankly, it takes me a lot of effort to work on every project when I work with architects and engineering firms to really look at, these, and some of these are very, very simple interventions and have great impact on the energy performance. And like I said, when you're looking at high performance buildings, you've got to start early. You cannot simply retrofit a building and just take a building which is built and already imagined and convert that into high performance. Yeah, over to the audience, and if anyone has any questions, I'd like to sort of take them up.
So there's Prabhat Kumar asking if we can share the research paper on effective fans.
I think that should be possible, Sandhya. I think IHS
Yeah,
probably has that, and I think that should
sure.
be possible. Yeah.
What actually stops people from using these small common sense strategies while designing? As from your experience, what is the biggest challenge which you think is
Yeah.
stopping from using these things? Because I'm sure everybody is aware of these simple things, and it's just a matter of translating it then
Yeah.
into the design.
Yeah, I think you've asked a very pertinent question, and I also sometimes wonder why, because they're so simple, so relevant, and some of them we have sort of experience in personal life, and we still don't implement them. So I think one of the key reasons is that a lot of the HVAC design we see is influenced by practices in other countries. So, for example, in Europe, in general, they do not prefer air draft, right? And so, you have MNCs or, kind of companies which are setting up offices here. So they're not used to seeing ceiling fans in their spaces there. In fact, it's not even encouraged in that in Europe. I think only in very few places in the US, you still see ceiling fans. And this is a very Asian or maybe a tropical requirement where you have heat and you have moisture and you want to feel that draft, and then that gives you a different feeling. So cultural reasons, I think, is one issue, because a lot of the practices come from other environmental conditions, and therefore, you know, for us, ceiling fan seems to be something new. That's one. Uh, for a long period of time, ceiling fans, at least ceiling fans, if I talk about, and we also struggle to integrate that in some of the projects, and people tended to feel that they were not aesthetic. And so that's a very strong pushback from architects and interior designers, where they say that it's not good looking. But I think if you see the last couple of years, you have a lot of good looking fans which have come out in the market, and I actually feel that they add now value to the decor, rather than they're no longer an eyesore. They actually become part of the decor itself. So that's something which is happening, but the general pushback against aesthetics. Some of the other things which I've talked about, like diversities, people are simply not aware, and I think people don't ask the right questions, because we get into a project, we start working on it, and we trust the HVAC designer to do something about it. The HVAC designer also assumes we don't ask enough of the user. So the more questions we ask from the user, the better answers we get, and the better sense we get of what is the actual method of operation of that particular facilities. Like I showed a university campus, but it may not be the same for a commercial building. It may not be the same for a residential building. So we need to ask these questions, and that is something which I think we do not do enough. We look at the last project, and a lot of our projects are copy paste. So we look at the last project and paste that into the next one, and the next one, and the next one, and so we at some point of time we forget that this was important. So things like diversity, and that's the big impact, a very, very large impact intervention, but missed out because we simply did not ask for it. We assume diversities, and that's even more dangerous, because all facilities may work differently, and assumptions lead to maybe an undersized equipment sometimes, or a very, very heavily oversized capacity, both of which are not healthy for the facility. So cultural reasons, I would say, copy paste for whatever reasons we do. And definitely, I think a little bit of awareness, and maybe the intent to integrate, rather than look at things, like for example, I talked about large ducts, and every project I worked on, we have this discussion and argument. And I now say that, because the impact is such, we start looking at building design to accommodate a duct which will be required, which is like, which we need to start, because we have to look at business designs very, very early. So that's very important. We get into engineering very late, and that's also a problem, where a lot of the opportunities lost by the time we get into it.
Great. So we have a couple of questions. I'll just read. Yeah. There is Karina Shah. She is saying, in terms of cooling methods, how much of an increase or decrease in percentage cost is incurred when water-based methods like radiant cooling is used in buildings?
a good question, Karina. And I've been involved in a few projects where we have used radiant cooling. And if you start really early, and again, I want to sort of make this statement so that people remember this, it's very important to start very early. If you start early, you might end up doing the same project at probably, depending on the scale of the project, if you're looking at 3 or 4 lakh square feet or 5 lakh square feet kind of a building, commercial building, you might not actually see a delta at all. If you're looking at a smaller project, you might see maybe a 5-10% kind of an increase. But the key here is to start very early. So if you make a building, if you've fixed everything, you've decided everything, and then decide to get into a water-based system, you will always end up spending more. So if you start early, you are able to now optimize equipment, reduce the capex, and therefore use it to offset some of the expense of a water-based system. In the overall, in my experience over several projects, I've done about 4 or 5 large commercial buildings with radiant cooling. I have not found that to be more than 5% more efficient, more expensive, even in the smallest of buildings.
Great. Mr. Kapil has a question. He's asking underflow cooling techniques is things of past or still relevant?
Yeah, underfloor is relevant. I think underfloor has underperformed, if I can say that, because underfloor seems to be very logical. You supply cold air from the lower sections of the floor, and then it follows the natural trajectory of heat. Very relevant, but it has not performed as well. There are some, again, in my experience, at least in India, I found some very unique problems which are probably not uh, seen so often in other places, like things like cleanliness, for example, because in underfloor you have a raised floor and you have diffusers on it, and people walk with wet feet, or people have muck on their shoes when they're walking on it, and this tends to make the underfloor cavities very dirty. So there are some issues of smell. In some projects which I have seen, there have been rodents in the underfloor. So these are all typical problems in India. I don't see this happening globally, but this is, I think, uh, one is this, and the other thing is also that the underfloor is not necessarily less expensive, because even with an underfloor, you still need to have a false ceiling. So as an overall project, it tends to become more expensive than even the radiant cooled system. So cost is another issue. But otherwise, technically, it should have been a system which should have worked very well. And particularly along with radiant cooling, it should have really blended together. But it has not happened for, I think, primarily the price reasons. Secondly, the experience which people have had wherever they have tried underfloor.
Great. There's Pranay. He wants to know what are your thoughts about effective ways of indoor air quality improvements within a space?
Uh, Brunei, right? Yeah. I think
Yes,
the
Pranay.
first thing, yeah, yeah, and I want to bring this slide up because I was, like we were talking about this in one of the workshops, and so I think the first thing we need to do is to identify your sources of pollution. And of course, not just external pollution, but also the sources of pollution within the space. And the most effective method of improving indoor air quality is to remove the pollutants as early as you can and as quickly as you can. I mean, as effectively as you can. And I think that's the, if there's a thumb rule or a sort of a golden guide, I would say work on extraction. Look at where the pollution is, where the pollutants are getting generated. Like in this case, you have the toilets, you have smell, and you have other, infectious organisms which might be present in that space. You want to make sure that it is quickly removed from a building. I think that should be a primary objective. And along with that, the location of these units. And I can't undermine the importance of this. We have so many discussions, and every project, the first thing we do and the first thing I look at is how we are locating the outdoor air intake, the fresh air intake, and the exhaust. This is extremely, extremely key because it is only fresh air that is going to dilute or going to make sure that the space is going to be better or the IOQ is going to be better. You cannot do it by any other means. So uh, when we're doing that, we need to make sure that nothing else is contaminating the fresh air which is getting into the space. So I would say placement of your outdoor air intakes, placement of your extraction fans, making sure the extraction is effective should be the number one and the most effective way of improving indoor air quality. Of course, we have ASHRAE giving us a formula, telling us how much should be done and all of that. But in actual practice, what will happen is, or what will really work is when you look at these small things, locating the service rooms right, and that will make a big difference. Making sure extraction works well, that is the really, really most important thing one should look for.
Samit, there's Anmol asking, can radiant cooling be retrofitted into existing building to make it a high performance building? If yes, what are the key considerations to be kept in mind?
So it is going to be difficult to retrofit that into an existing building because it depends first on the scale of the building. I think that is something which you need to keep in mind before you decide radiant or non-radiant, because you will not in radiant cooling, if you have some idea about that, you will require two sets of cooling temperatures, one which will remove moisture and one which will just remove the sensible heat from a space. So in a building, it is always in an existing building, it's difficult to integrate another uh, chill water system if the piping has already been done. So it's not easy to pull it off. Let's say if even if you are able to do that, you need to look at the scale, because smaller buildings are very difficult to pull off. You don't need equipment which will give you higher temperature chill water in smaller buildings, smaller capacity. So that is a concern which you'll have to watch out for. Since it is an existing building, you'll have challenges of like you cannot, for example, embed a radiant pipe into a slab because it is an existing building. But you could look at other techniques which are available, like radiant baffles, radiant ceilings, which are suspended like a false ceiling. But in all of these things, because we're starting off in a project or a building which is already ready, the cost is going to be very high. So that is going to be third, barrier to trying that. Having said that, I mean, nothing is impossible. It's a lot of, look at probably how you can integrate a new chill water system, how you can bring that chill water, which is a different temperature loop, into the space. If a building which is existing does not have sufficient shafts, these are all going to be issues. And of course, in the end, your costs are going to be high, so you'll have to evaluate that before you propose this to a client, or you consider that within your own project.
Great. Uh, we have Prananjay asking, what are the key challenges associated with implementing these strategies when constructing in taller buildings?
So yeah, so tall buildings, like I said, I was talking about one of these uh, options here, and you can see that tall buildings nowadays, people have tended to move the toilets to the core, and this is an issue because it seems to be spatially more elegant and is also spatially more efficient, but it is uh, not effective at all when it comes to extraction. Like I was talking about the importance of extraction. When you look at tall buildings, it is very difficult to make sure that the all the floors will be extracted equally, and the air from all the floors will be extracted equally. If you have the extraction fan on top. So one of the most important things and challenges which I see is the location of equipment. And the taller the building is, the more the potential diversity in a building, right? And if you have a multi-tenanted building, then you can expect that many of these floors will not be operational at any point of time. So you need to build in flexibility into whatever system you're looking at, radiant, non-radiant, edge, whatever that system may be. You need to look at flexibility. You need to look at capability of the system to be able to react to business demand. So that is another important thing which we need to look at. Of course, tall buildings have pressure, very high pressures across the height of a pipe. So you need to break them at different levels. I'll not get into the technical part of that in this common sense webinar, but you'll have to look at the engineering of the pipes very, very carefully, because you'll have a large column of water, a tall column of water, and the standing pressures may be very high. You might have to split them every few floors so that your equipment is safeguarded. So some of these things which I can quickly say, but in general, I feel all of that which can be applied. And we're talking of buildings. We've worked on buildings 10, 11, 12 floors, and that can also be scaled up. Uh, but most essential is to look at, again, I would say, how do you get air in, how do you take air out from the space. So whether it's tall or short, then it actually doesn't matter, because every floor is just another office.
Okay, Sandeep is asking that you've talked about extraction, but is it really used in commercial buildings? We don't even check the positive pressure in conditioned spaces and hence reducing infiltration. How important this is to be checked?
Well, absolutely, and you're right, Sandeep, that is not checked, and that is why it is on my list of strategies which should be looked at. And I mean, the this video or this image should stay in your mind. This very, very simple, uh, very easy to understand, and it exactly works like this in a building. So if extraction is not done, you cannot bring in air. However, our calculations may show something. You might have a fan which is supposed to be doing that, but it doesn't happen. So it is essential to make sure that the buildings are slightly positive. I would say infiltration, I mean, is something which we have not looked at all. But because the extraction and pressure is not always matched, we have infiltration uncontrolled in most of the office building. But something which I always emphasize that should be checked. So you can have actually different differential pressure sensors in a space to check how the space is behaving with respect to the ambient. And I would strongly recommend that at least in tall buildings, high performance buildings, we definitely need to check that. We need to know where from where you're getting the air in. If you have more extraction than the air you're supplying from the air handling units, then you'll also have negative pressure in the building, and then you will start getting air uncontrolled and unfiltered into the space, which is also an issue. So you would want to make sure that they come through the air handling unit where you have the filtration mechanisms available, and not from leaks and openings which are not controlled. So uh, essential in my mind, absolutely essential, should be built into every building, and certainly a high performance building should know where it is getting its pressure from.
Thank you, Samit. Any strategies on how to integrate large ducts in traditional beam and column structures?
No, in very difficult in existing buildings. And if you've already decided what should be your floor to floor height and what should be your uh, you know uh, beams and the depth of the beams, it is very difficult to integrate large ducts after that. So like I said, you have to start early, because the impact of large ducts is so much, and because it has so much of impact on the energy consumption. You need to start looking at what should be your floor to floor height to be able to accommodate a duct which will give you efficiency. So you don't start by saying that this is my building height. You don't start by saying that this is my beam height and now accommodate ducts within them. It's not possible. You cannot, sometimes I have this discussion and people suggest having cuts in the beams and all of that. I've never seen any of them work. That sounds like a cool concept, but when we get into actual structural design, you will realize that the structural engineer will not let you do large openings in the beams. So in the end, the only option you have is to go below the beam. And therefore, if you want to accommodate a large duct, you need to look at the space you have below the beam, space you have below the column capital. And if that is not enough to give you the experience you need to start considering higher floor to floor height. There's no shortcut to this. You have to start early, and that should be built into the architectural section itself.
Um, the next question is, what are the critical things one should consider in conceptual stage of a structure while planning, designing to make a building thermally efficient?
All right, so I think you have a lot of webinars on that, Sandhya. You do.
Yeah.
So yeah, so I think is there a plan for or a series or a sort of a calendar of events which they can. I would
Yeah.
really love them to. I really love them to have a look at some of these webinars which are being arranged by Assure as part of the Assure program because there's some very good content on these webinars. And I think the workshops also, if you're in one of these places where the workshops are happening, I strongly recommend that you look at these workshops. There's good learning content also available. And I strongly recommend going through that learning content. It's very rare to find all of this content in one place. It's very nicely curated by IIHS and the team here. So I would strongly recommend that you should do that. And that should give you a lot of good ideas about how to optimize the building. Of course, we are talking of HVAC today, active HVAC systems today, but before we've gotten to this stage, you should have optimized your building, right? So, and I always say this, a very well designed envelope is the best HVAC equipment you can have, and you can't do anything better than that. So, uh, if you have not done that, equipment efficiencies in this industry may vary by about 4 or 5%, but almost 50% of the impact of cooling load, of 50% of the uh, you know uh, I would say the s- the impact is controlled by passive design, and that should have happened before you reach the stage of active HVAC design.
Um, Sarang wants to know that do pipes embedded in walls and roof or slabs have chances of leaking or bursting in radiant cooling mechanism?
So we've used pipes which are embedded in ceilings and slabs, and they don't burst on their own because these pipes are very well, they're designed for such pressures. And the only risk is when someone drills into them. So on their own, these pipes they have, like for example, some of the pipes manufacturers I have used, they have a 100-year life, so they don't easily burst. And they are encased. If you're doing it in a slab, they're encased in slab, so they're actually very very rigid, very well protected. What you need to just make sure is that someone doesn't drill into it after they have been implemented in a project. So you need to mark them out, or someone should be aware that a certain slab is carries a chill water pipe, and therefore you to be careful when you're adding services. When you're doing a building first time, people will be careful, but when adding services later or modifying some things later down the line, 10-15 years later, you need to make sure that people are aware of that. If the care is taken, then you don't see these issues. It's the joints which one has to be careful about. So you don't have joints in the slab, so you have all the joints outside the slab. So if there is a leakage in the joint, you can also see it and fix it. Usually these pipes don't burst unless someone drills into them.
Yeah. Pranav says that in many of projects, you know, getting some kind of a clear height, especially in driveways or car parks, is not possible.
Yeah.
So reducing the height of ducts is difficult. So what kind of strategy can be used if you are not getting the clear height
So
to reduce energy consumption or loads in such cases?
yeah, so let me just, this is one idea, and I use this quite frequently. So this is one arrangement which you talked about, one single AHU for the entire office, and you have two toilets here. And this is another arrangement, maybe this is another arrangement where you have two AHUs, smaller, but for the same office. So what happens when you use smaller air handling units is that you will actually end up having smaller ducts. So this is what I was talking about when I refer to distributed systems. So distributed systems can actually let you have smaller ducts with the same area. And as you can see, because you have two air handling units, you have the duct runs are also shorter, and therefore you're going to be more efficient, right? So it's also not true that because you have now two air handling units, therefore you require double the space. Usually it doesn't happen. You might require a little more space than one air handling unit, but certainly not double. So if you optimize air handling units, scale them down, and also try to optimize the space around it, you might end up with a probably about a 50% increase in service space. But then if you don't have height, then this is another way of doing things. So use smaller equipment, reduce duct length, and then that will let you do smaller ducts as well. I have used this also very, very effectively in many projects. And one of the important parameters which we tend to neglect, and something which is becoming very, very important, is noise. And we tend to look at energy consumption and temperature, thermal comfort, all that is fine. But noise is becoming more and more an important design parameter. And when you have ducts which are, or systems which are distributed, smaller AHUs and shorter duct runs, you also end up having a quieter system. And you will find a lot of modern offices are demanding, users are demanding this, something which we, I think should be looking at, if you're looking at commercial spaces in the years to come.
So, Samit, I am going to ask you last questions. One is sometimes you're not aware of who the user is.
Yeah,
So, you tend to do a safe design
yeah.
because you don't know application of diversity, the use, especially these kind of tenant commercial buildings. So, in this case, what would you advise? How do intelligently can we use some of the strategies?
I think flexibility is key. In my mind, I think we should be trying to build flexibility, because even if you know a client, the building use might change. So I think flexibility is key. Building flexibility into the design is something which is very useful. So interior design is that way always, they factor for flexibility while planning. But systems have traditionally not been thought about as something which has to be flexible. I think that is something which is becoming more and more important. And I would strongly recommend the looking at systems from a flexibility perspective, not just from a space saving perspective. Of course, when you're talking about flexibility, like for example, in this office, which I'm showing on the screen, you can actually split up the office, entire floor, into two offices as well, right? So this is something which can be done, uh, and it is important, like I said, to ask questions and as far as possible to get a more qualified understanding of what are processes. I find in my experience that if you ask questions of your, even if it's a developer who's building making a building for his user, I think if you ask the right questions, you'll get some sense of what that building has been constructed for. At least 80-90% of these things can be figured out, I feel, from asking the right questions. Uh, Most often, we assume that we will not get the answer. This has been my experience, and we feel that I'm not going to get it, so let me assume something and go ahead. Or it is going to take time to get a solution or get the answer, and therefore we don't ask. So we assume and move ahead. But I find, or of course, if you've done commercial offices, you've done a few, then you'll also know how to handle these situations. But I'd still strongly recommend talking to your clients to find out what the general idea of this thing is. If that is not available, even after you've done that, then I would say look at flexibility, look at systems which can be scaled up in stages, like modular systems. Like, for example, if you have a chiller plant, rather than doing a very large chiller plant on day one, look at how you can scale it up in stages, because you do not know what's going to happen next.
Right. Before we close it, last question. Samit, how do you define high performance building as per you?
All right, so that's good, Sandhya, because and I'm going to give this my own definition, so not not what I would see, because high performance always tends to mean, and we talk about high performance, and always we only think about energy performance, and I think that's not entirely the definition of high performance. I think high performance is not only something which is efficient, but something that is very user friendly, or where some place where or a space where the user experience is also good. by using the word user experience, I'm also now bringing in these elements of noise. I mean, bringing the elements of indoor air quality, which tend to get sidelined when we talk of high performance. Typically we're just looking at energy performance and just that aspect of buildings. But I think it's not enough to have a very efficient building, but not have good indoor air quality. So as important as energy performance is, I think it's extremely important to give good indoor air quality, extremely important to give a good user experience. And in the end, I think good user experience will drive, the definition of high performance.
Well said. Thank you so much, Samit. We have a couple of questions, but we are running out of time. I would really encourage each one of you to be a part of our immersion workshops where you can actually have a face-to-face chat with Samit, and then you can use all his time to ask more questions. Thank you so much for all of you. And thank
Thank you,
you
everyone.
once again, Samit. The link to the Mumbai workshop is already pasted in the chat. Please register and be a part of this. There's a great learning. Thank you very much for your time.
Thank you, everyone. Thanks, Sandhya. Thank you.